Got the captions going. All right. So, can you guys all hear me? Okay, good. There you go. So we're gonna start today by talking about integrals. That's what we're gonna spend actually the whole week doing is integration. Can anybody in one word sum up what derivatives are? If you had to put them in one word in the chat. Actually, I want everyone to try this. You can use, actually, you know what? You guys can use up to 4 words. I want everyone to give me in 4 words or less what a derivative is, like in its essence. So I got slope, I got rates, I got instantaneous rate of change, I got slope. Yeah. Yeah, slope of the tangent line. Yeah, that's really what a derivative is. So in calculus, there's 3 things we do. We evaluate numbers, that's limits. We find slope, that's derivative. And the only thing else we're going to do, well, in calculus 1, is we're going to find area. So it's broken up into those 3 components: numbers, slope, area. 6th grade, 7th grade, 8th grade. That's it. So that's all we're going to do. We're talking about an area and what it is and how it works. If I told you you drove at 5 miles an hour for 3 hours, how far did you go? You drove at 5 miles an hour for 3. Okay. 5 miles an hour for 3 hours. How far did you go?
15.
Yeah, 15 miles, right? 5 miles, you multiply, right?
Mhm.
So this is kind of how this works. Is the integral is the area under the curve. So if I made this one rectangle, the function is the velocity graph. And notice that if you find the area under the velocity graph, that's your distance traveled, right? What was the relationship between position and velocity? I know we didn't talk about it too much, but velocity is the blank of position.
Antiderivative?
Almost, it's just the first derivative.
Oh.
Remember, a derivative is a rate of change. So velocity is how fast your distance is changing, right? So then if we reverse it, if you integrate your velocity, that tells you how much distance you've covered. Okay, right? So if I want to know how far I've gone if I drove for 7 hours or 8 hours at 5 miles an hour, 5 times 8 is 40. Right? And it's pretty easy when it's a constant function because it's just you just multiply and you're all done. Now, what if my velocity changed? Right? What if my velocity was equal to like y equals x? I move this, can't move this. Right? What if it was equal to like y equals x? And I traveled for 5 hours. So if I can get this thing to show that, there we go. So during the first hour, I went about 1 mile an hour. But then by the second hour, I was moving at about 2 miles, or exactly at 2 miles an hour. So then at 3 miles an hour, or 3 hours, I was going 3 miles an hour. So as time goes on, I go faster. And if I go faster, it's going to mean I do what with my distance?
Increasing your distance.
Yeah, the faster I go, the more distance I cover. Right? So you can't just do like the, left, right minus left, or multiply them. So if I have this, why is this not working? What is P? Oh, there we go. Would that give me the correct distance traveled? No, you see I have all this extra stuff. I only want the area under the curve. So what I'm going to do is instead of just looking at the entire interval, here's my camera, I'm going to split it up. And that's going to give me a more accurate representation of my area. So then I can just continue that process until what? So how do I make it more accurate?
You get those rectangles very small.
Yeah, and I think I just broke it. But yeah, so you get your rectangles to be, oh, there it went. We'll just say 1,000. And you'll notice how now there's no extra. So this is the whole idea of integration is we're finding the area under a curve. Now this one's easy because you could actually just find the area of this rectangle or this triangle using a triangle formula. But what if it wasn't that easy, right? What if it was something like x squared? Right? And I want to integrate from, let's just do 0 to 4. Because it's not a regular shape, we can't use like a regular shape. So to evaluate it, so like what you're going to do is we're going to make more rectangles. And so on until we get a more accurate. And what we're actually going to do is we're going to find the area of each one of these rectangles and then add them up. So it's not so bad if you only got maybe like 8 rectangles, but what if I have like 80 rectangles? Like, bro, I don't want to do that, right? It's too much work. So that's where integration comes in. And another thing I want to show you is we have 2 kinds of approximations. We have like 4. We're going to talk about the first 2, which is right rectangular area method and a left rectangular area method, or LRAM and RRAM. Notice that when I move this, this RAM focuses on the right endpoints. I'm sorry, the left endpoints. Left. If I move them over here, it's left endpoints because they shoot out from the left of the graph. And then you can actually do something called MRAM, where you look at the center points. MRAM is going to be more accurate than RRAM and LRAM because it averages them. All right. Oh, you guys can't see anything? You guys can see it, right?
Yeah.
Oh, okay, because I've been talking for like 5 minutes, and that would have been embarrassing. All right. Just the concept of an integral is the area under a curve. I want to know, did that make sense? 1 through 5. So the integral is the rectangles under the curve. Even if you don't know how to solve it, you don't know how to do it, just that concept. Okay, cool. Looks like most people got that. So again, that's what we're going to be focusing on for this whole entire week, is evaluating them and working with the concept of an integral. So remember last week when we did derivatives, we spent the whole first day just learning the rules, like learning how to add, subtract. And then on the next day, we like put into practice. It's going to be very similar to that today. So boom, boom, boom. Here we go, integrals. Put you guys over here. Also, congratulations, you just finished your first week of integrals. Like, I spent a week on that. Just that one topic. Okay. All right, so we're going to have a particle starting at t equals 0, so it's starting when time is 0, and it's going to move along the x-axis. So basically, it's just going to move left and right. With the velocity of t squared, where is the particle when t equals 3? So the first thing I do is I'm going to graph out t squared. Right? So if I want to know where it is after t equals 3, I need to find the area under the curve. And we're going to do that using LRAM and RRAM. So LRAM, which stands for left, I don't want to write RAM out, rectangular area model. So I guess I will, rectangular area model. And what that means is we're going to break it up. We're going to break this up into 3 subcomponents. We're going to get 3 rectangles. So if I break up 0 to 3 into 3 rectangles, what's my delta t? What's my distance if I break it up into 3 equal subintervals?
No.
3.
Yeah, 3, right? Yeah, so I'm going to break it up into 1, 2, and 3, right?
Okay.
So if I see, how do I word this? If I were to make a chart or a table and I separate it into 3 rectangles, I actually get 4 coordinates because each rectangle needs 2 coordinates for a base. So here's t squared, and you get 0, 1, 4, and 9. So I get the point 0, 0, 1, 1, 2, 4, and 3, 9. So if rectangles need 2 points to make it up for the base, LRAM, we're going to do it in blue, uses the left point. So my first left point is this, and there's my first rectangle. It has a height of 0. Here's my second rectangle. And then here's my third rectangle. Right? I'm using the left points. So I'm using 0, 0, 1, 1, and 2, 4. Those are the heights of my rectangles. Okay. So for LRAM, it's going to be delta t times y of t naught plus delta t y of t1 plus delta t y of t2. Now, what in the world, right? Does that even mean? All this means is you're going to plug in your t values into your equation. So what's my delta t? What's the horizontal distance of each rectangle?
Which one?
It's 1. And then my first input is 0. So then it becomes 0 squared plus 1, 1 squared plus 1, 2 squared. So I'm taking that output or input, sorry, and I'm plugging it into my function, which is t squared. So I get 0 plus 1 plus 4, which is 5. So that means if I add up these rectangles, I get an area of 5. So that's called a left rectangular approximation. Okay, now we're going to do RRAM. And that stands for right. All of that. Rectangular area model. And that just works a little bit different. Instead of starting at the left point, we start at the right points. So I'm going to use 3, 9 to draw my first rectangle. Then I'm going to use 2, 4, and then I'm going to use 1, 1. So this represents RRAM. So again, it's delta t times y values. So my delta t is equal to 1. So it's 1 times 9 plus 1 times 4 plus 1 times 2. So that's 11, 15. 14? $15, right? Not everyone help me at once. 15? 14? 18? 22?
15.
What? Yeah, 15.
So the area underneath is the speed? No,
Distance,
no,
distance.
the distance, the distance.
Mm-hmm. Now, so obviously one is an over approximation and one's an under approximation. Using the rectangular area method, they're going to be approximations. Now, how would I make it more accurate?
Subtract.
More rectangles.
More rectangles, more rectangles. Subtracting them really doesn't
Yeah, it doesn't do, yeah.
doesn't do anything. Technically you can average them. So like a closer approximation would probably be 10. If you did MRAM, you would get somewhere closer to 10. But yeah, you want to make the number of rectangles increase. Now we don't have time to do that by hand, but doing like 4 or 5 rectangles, no big deal. All right.
I'm sorry, how did you get 9 and 4? It's as a value. Okay, I get it. Okay. But really, it's Um,
Because this value here, this one, is the height. So notice that the height here is 9. The height here is 4. And the height here is 1. Because those are the outputs of the function.
okay, so, so
think you
in
went
the,
backwards, right?
under that curve, you were using the function.
I used LRAM. They both use the function. One's an overestimate and one's an underestimate. Even though the green rectangles are technically above the curve, we still consider that the area under the curve.
Oh, you're taking the whole thing, 1 over, okay, I get it, okay.
Maria,
1,
did you have a question?
1, 4, okay, I get it, thank you.
So I think that we were confused just because I think in the beginning you went from left to right, and then for the RAM you went from right to left.
Oh, yeah, I
Those are the
typically,
values.
yeah, I do that because you skip the first value with RRAM. So I always find it easier just to start at the end and work backwards. So I'm like, oh, wait, did I do the right ones? All right. So the big thing I really want you to get here is that total distance or distance traveled is area under the curve. We find that by approximating with rectangles. That's the big concept. Okay. Sometimes we don't need RM and LRAM because we have geometric shapes that we can work with. So a particle starts at x equals 0. That's too easy. Let's say a particle starts at x equals 4. I'm changing it. So if you have my notes printed out, I'm changing that to a 4. Not a 0. Okay. Where is the particle when t equals 6? If the velocity equals 1/2 t. And what that means is as time goes on, you're going faster. Think of it as you're leaving a stop sign. Slowly. So what we're going to do is the first step is to draw it out. So 1/2 t, I don't know, looks like that. Right, this is v of t equals 1/2 t. These are v values. These are t values. And I'm going to go all the way until 6. So I don't know, 6 is right there. That gives me the value of 3. Close enough. So if I want to find out the distance I traveled, your distance from start is area under the curve. I know that English is kind of broken. If the distance from your starting point is the area under the curve. And we'll talk about too what happens when your curve goes negative, because that's a thing. So if I wanted to find this area, what shape does this make?
Triangle.
Triangle. So instead of using like RRAM or LRAM, I can just find the area of that triangle. So what's the area formula for a triangle?
Base times height times 1/2.
All right. So the base is going to be 6 and the height's going to be 3. So that gives me a nice 9. So that means I'm 9 units away from where I started. So say it was in feet, I don't know, I'd be 9 feet away from where I started. This is not the correct answer to my question, though. I've traveled 9. And what I mean by that is from wherever I started, I'm now 9 units away. But did I start at 0? What was my original X position?
4.
4. So when t equals 6, the particle is at x equals 4 plus 9, which is 13. So you have to take into account where it started, because you can start behind the origin, right? If you need to put it in real life terms, think about when people run a race around a track. They start in different starting positions. So a 400 meter, that's the reason they have to do it. If they all want to end in the same spot because one of the rings is shorter than the others, it's going to have to start further back than other people, right? Because of the how long the rings are and things like that. And with a poll real quick, I'm gonna ask you see if this made sense to you guys. What's up, Sophia?
So basically, you take, you use this area of this triangle because, and then you add it to the position it was in the region, if it starts at 4, that means you have to add 4 units to it. If it
Right.
starts at 3, you would add 3 units to that triangle, which represents the position.
Yeah, that's exactly it. So I'm gonna reword it really quick, and then Alex, I think let me reword it, and if you still have the question, then yeah. So the area under the velocity curve, I know it's a straight line, but we still call it a curve, is the distance from starting point. So that means that the area under that curve was 9. That means if I started here, I am now 9 units away from where I started. So if I looked at this like on a number line, and 0's over here and 4 is over here, I'm actually at 13. And since everything was above the x-axis, I've only moved forward. Joyce, did that make sense? The reason I had to add 4?
So in a problem, if you're asked, so you basically figure out from the 0 to another point, and then if you start somewhere else, you have to add that position of the point, right?
Right.
Okay.
Okay. So there's 2 things going on here, which is one of them is time. Your input is time, but time can dictate a lot of things, right? Your position can change, your velocity can change, and your acceleration can change, all dependent on time. So I want you guys to imagine you guys are. Does everyone know where San Diego is? Not precisely, but does everyone know relatively where it is?
Yes.
It's south of Los Angeles, in case you didn't know. It's like near the bottom of California. Now, if I drove 100 miles north, so I drove 100 miles an hour for 1 hour. So my velocity curve would be 100. My velocity curve would look like this, right? And I'm starting in San Diego, and I go for 1 hour. I've traveled 100 miles. And let's just pretend that Los Angeles is 100 miles from San Diego. I would be in LA, right? Now, if I started in LA and drove 100 miles, would I still be in LA?
No.
I would be 100 miles further. And that's the idea. So if we started at 0, 0, and this was our velocity graph for t equals 6, my position would be 9. If I started at 0, 0, and I followed this curve and all of that, my position at 6 would be 9. Because it would be my starting position, this one, plus this. Now, if I started at, let's say I start at the position 0, 5. At time 0, I'm at position 5. My final position is 5. Well, technically it's not x of 6. Technically it's the area under the curve plus that. So it's this. which will equal 5 plus 9, which is 14. So the idea here is this is your change in X plus your starting position.
But X is T, and so now I am very confused and.
X is not, so X is in terms of T. But hold on,
Ah.
Alex has had his hand up for a while. Make sure.
Yeah, so basically the x function is the antiderivative of this velocity function.
You got it.
So that's how they're related, right? Okay.
Yeah,
That's fine.
so let's think of it this way. Let me try to explain it one more time, one more different way, and then we'll do more problems. So if I have my change in X, do you agree that's my final position minus my initial position?
Yeah,
That's the change. So the change in X, you can also think as the integral of the velocity curve. Because when I integrate velocity, that tells me how much distance I've changed. My change in X, that's my integral. Now, if I move this over here, I get my final position is where I started plus the integral of velocity. So if you integrate velocity and add your initial position, it gives you your final position.
okay, that's.
All right, let's try another one. Let's try another one. So same problem, but a little different. We're going to do this we're going to make this 2 problems. Part 1, start at 0, 0. Part 2, start at x of 0 equals 10. That second one is just, this is the same thing, x of 0 equals 0. Okay. So step 1, when you want to do this, is you got to draw a velocity curve. So we just draw a curve. And 1/2 plus 2 looks like 1/2 t, but then shift it up by 2. So it's going to start here and go like that. And this is 6. So when t equals 6, that's going to be, I think, 5 is the output. I think, right? Yeah, okay. So we draw a line down. So now what we have to do is we actually have to find all of that. Now there's 2 ways to do that. Well, there's a lot of ways. 2 main ways I've seen it done is you can either split it apart as a rectangle and a triangle and add them up, or you can use trapezoid formula. It's up to you. I'm going to go ahead and use the trapezoid. So the area for a trapezoid, and this is how I draw my trapezoids. Area of a trapezoid is h over 2 base 1 plus base 2. If you don't want to do a trapezoid, you don't have to. You can do a triangle and a rectangle. This is 6, this is 2, and this is 3. However you'd like to do it. So my height is going to be 6. Base 1 is 2, and base 2 is 5. That's base 2. That's base 1. And that's h. So you add all that up, and you get a nice 7, 3, 21. Now in the chat, I'm going to give you guys 20 seconds. And I want you to type in, do not push enter yet. I want you to type in, what do you think that 21 represents? And I've got 2, 4, 6, 8, 10 people, at least 10 people here. I want at least 10 responses. Do not type anything in yet. I forgot I totally have a button for this. It's somewhere. There it is. Hold on. Time doesn't start till I get this thing to work. Okay, in the chat, 20 seconds. Do not push enter yet. What do you think that 21 represents? Your best guess. I didn't say to push enter yet. You got 7 seconds. Spoiling it. All right, go ahead, everyone, push enter. Oh no, the noise. Oh, I don't know. I forgot about that. How do I stop it? Okay. All right, so I've got. Let's make this chat nice and big so I can read it. Distance, new position, distance, the position at t equals 6, and the change in distance, distance traveled, total distance traveled, distance traveled. Yeah, so the 21 is your change in x. It's your change in position. I've changed 21 units from wherever I started. And the cool thing with integrals, it does incorporate going backwards and forwards. Now, in this case, we're only going forwards, but I'm 21 units to the right of where I've started. So in this case, x of 6 is just 21 because I start at 0. In this case, it's 10 plus 21, which is 31. So x of 6 is 31. Right? Because I started at 10 and then went to the right by 21 units. So let me see if that makes sense. Let me know if 1 through 5, the idea of you have to add your starting position. Let me know if that kind of makes sense to me. All right, cool. We're getting there a little more. Awesome. All right, you guys ready to start week number 2, or I guess 3 technically, of integrals? Here we go. I'm gonna go fast. You will not have time to draw all of these. I'm gonna preface that you do not have time to draw all of these. Okay. Over and under estimates. If you have a decreasing function that is either concave up or concave down, it does not matter. LRAM is going to be an overestimate and RRAM is an underestimate, no matter the concavity. Concave up, concave down, or no concavity. Decreasing functions work this way where LRAM is over and RRAM is under. Conversely, increasing is the opposite. Right? LRAM is underestimate for increasing and RRAM is an overestimate for increasing. And the way I remember it, because I always forget, is I just draw a line. Concavity doesn't matter. Right? If I want to do RRAM, I start at the right and I go left. Does that make sense how I did RRAM? It starts at the right and then it shoots left. And you see for increasing, it's over. LRAM is the opposite. You start from the left and shoot down. Does that make sense? And so that's the idea. If I ever forget, again, oh no, my function looks like this. Okay, RRAM goes this way. And you can see right away how it's under. And then LRAM, it's going to be over because it shoots like this. So I don't actually memorize any of those. I just really quickly draw something and then draw the rectangles and go, oh, it's over under. Because it can ask you a question like, was this approximation an over or under estimate? And so that's kind of, you would go, oh, the function's decreasing, so it's blank. And so that's kind of how you do that. All right, sweet. All right, notation. Let's talk about this. It's a lot of math here, a lot of math looking things. And I'm going to warn you, if you're going into teaching, this symbol, be very careful saying it. Anybody under, I think, 30 will get that joke. Very, very careful saying that. Because the second you say it, the kids are going to go nuts. So the way this reads, well, where'd it go? Is the limit of the summation of the area of the rectangles. Or sigma rectangles. And that's a new word for kids. Because if you think about it, that's a y value, and that's a horizontal distance, right? So if you multiply the y by the horizontal, that's where the rectangle comes from, right? Your rectangle is made up of y delta x. And this symbol in mathematics means to sum. This is the sum symbol. So I'm summing the areas of the rectangle, and the question is, how many rectangles? An infinite amount of them. Look, limits are back. An integral is just a limit. All we're doing is adding rectangles. That's all integration is adding rectangles. So if you ever like math too hard, just think about all we're doing is adding rectangles. Okay. This translates into this. Your delta x becomes dx. This becomes your function, and a and b we'll talk about where those come from. So it reads the integral of f of x from a to b with respect to x. We always read the bottom limit first. And delta x, if you had to evaluate it, is b minus a over n. That's how many, n is how many rectangles you have. Marie, you thought what was distance? I just saw that.
Just the underneath the curve for the last problem.
Oh, it's the change in distance.
How would I know if it's the change in distance versus the distance? Just because the previous problems were distance.
Area under the curve is always, well, not always, but area under the curve is the change in distance. If you start at 0, it's also the new distance, because like, since you started at 0, 0 plus the change is just going to be whatever it is.
Okay, thank you.
Okay. So what I want to do is I want to rewrite this summation as an integral. I'm going to rewrite this summation as an integral. And your limits right here, that's a, and that's b. So ready, set, here we go. And how do I know it's an integral before I even, am I allowed to write it as an integral? How do I know?
You're summing up infinite number of rectangles.
Yeah, this is what's telling me it's an integral. I'm finding an infinite sum. That's what that's the literal definition of an integral. It's an infinite sum. And next week we're getting to series and sequences when it's too hard to evaluate with these integrals, and we have to use series and sequences. So this becomes the integral. A goes on the bottom, b goes up top, and m sub k just becomes x. And we're done. That's it. Pretty easy, I think, writing a sum as an integral. Think so, right? Yeah.
So why, what was m again?
M sub k right here.
Oh, it's a summation. Okay.
This is m sub k.
Okay.
All right.
So then you just, okay. And then
Evaluate.
it comes,
and,
okay.
and I'm gonna teach you rules how to evaluate that in a little bit. All right. This one's a little different. I like this problem because it really reinforces LRAM and RRAM. It says find the distance traveled on the interval 0 to 10 by evaluating the integral from 0 to 10 v of t dt. But I'm not given a function. I'm just given a table of values. So what we're going to do is we're going to actually plot all of these values. So we're going to take a minute. And we're going to plot all of them. 2, 5 is like right there. 4, 12 is like right there. M sub k was, yeah, it was like the function. M sub k represents the term. So if you looked at it, it was m sub k squared at times m sub k. M sub k means evaluated at a specific k value. Because that's how a summation works. You plug in k equals 1, k equals 2, k equals 3, and so on. So it just gets replaced by x. 621 is like right there. 8 comma 25 is like right there, and 10 comma 28 is like right there. Close enough. And as you can see, like if you were to try to make this a curve, it would look something like that. Like good luck, right? Finding the equation of that. And so we're gonna approximate using Riemann sums. And this is really applicable to the real world problems, because often in the real world, you aren't given a function. You have recorded data sets, right? If you wanted to find the distance traveled of a car, you could like measure with a time watch every time it goes, you know, a certain distance or a certain speed, you know. So you could be talking to someone on the phone and be like, all right, after 2 seconds, all right, how fast are you going? After 4 seconds, how fast are you going? And then plot the points. Okay, so we're gonna use this doing LRAM and RRAM. So let's do LRAM first. So LRAM is going to shoot from the left. So I start here and it shoots this way. Right? It's going to start at 0, 0, and it's going to shoot that way. Then it's going to go to 2, 5, and it's going to shoot this way. Then it's going to go this one, and it's going to shoot that way. Then same thing. Same thing. Does that make sense? You start at the left points and you shoot to the right until you get to your next t value. Okay. So what is my delta t?
2.
2. And it doesn't have to be the same every time. Just so you know. And you find that by subtracting those values. So it's 2 times, this is let's say I was doing LRAM. What's the first height?
Yeah, 5.
Almost. Wait, remember our
Oh,
first
0.
point started with
0.
0.
0.
Yeah. So it's actually going to be 2 times 0 plus 2 times, what's the next height?
5.
Okay, what's the next one?
12.
And we're going to keep doing that process one more time till 25. I do not include 28 because I do not have a rectangle of height 28. So this is going to be 10, go away, 24, 42, 50, 34, 92, 6, 126. Yes. All right. That means I've traveled 126 feet, because notice my velocity was in feet per second. All right, that's LRAM. Now let's do RRAM. RRAM. That's going to start on my right points, and it's going to shoot to the left. So there's my first rectangle. There's my second rectangle. Third rectangle. Fourth rectangle. And fifth rectangle. Okay. Same process. Delta t times the height. Delta t, or the width of the rectangle, times the height. So it's going to be 2 times, and for RRAM, I like to go backwards. I start this way and I go that way. So 2 times 28 plus 2 times 25 plus 2 times 21 plus 2 times 12 plus 2 times 5. 56 plus 50 plus 42 plus 24 plus 10. So 106 plus 30, 76. 1, 2, 8. I think I did that right. I don't know. We'll never actually. All right. Now, so that means using RRAM, I went 182 feet. So I probably actually went about 150. Right, if you average them out. Cool. All right, that's LRAM and RRAM in a nutshell, and how to use them. Let me see how we feeling 1 to 5. If I asked you, either gave you a function or gave you a data set, would you be able to find the approximate distance?
I just have a question.
Sure.
How you drew the first rectangle from the 10, or but you are using the 28 one, right?
Yeah, yeah,
The
this
10,
is, that's 28, yeah.
and you didn't use it in the LRAM.
Correct. LRAM excludes the last point,
Okay,
and RRAM excludes the first point.
which is, okay, so that is important, okay.
Okay, awesome. All right, you guys ready for your rules for integrals? They're very similar to derivatives, but let's talk about them. So for definite integrals, if you flip the limits of integration, so you flip the integrals, you just put a negative in front of it. That's it. Okay. Rule number 2, and this one is like kind of one of my favorites. If you integrate from the same x values, your integral is 0. Who thinks they know why? If I integrate from 5 to 5, why is my integral equal to 0? Yeah, as my God in the chat. Yeah, I have no area. I have no
Yeah.
width. I can't make a rectangle. There's no width.
Oh, yeah.
So that's why it's 0. So if the limits of integration are ever the same, it's just 0. Integrals also exhibit the constant rule. Constants can just get right out of the integral, just like limits, just like derivatives. Just like derivatives, an integral can distribute over addition and subtraction. And just like derivatives, they cannot distribute over multiplication and division. What's cool about integrals, actually, if you integrate from A to B and then from B to C, that's the same thing as the integral from A to C.
Yeah.
Right? Because if I show you graphically, here's A, here's B, and here's C, and there's my curve. If I integrate from A to B, that's this. And then from B to C, that's this. That's the same as me integrating from A to C.
So it's summative.
And what's cool about integrals too, they don't care about discontinuous functions, like at all. Like not in even wholes, like they could care less, because think about it. If I have my integral, here's my function, and I want to integrate from A to B. All right, so that's going to be this, right? And then you just keep going. Does it matter that it jumped? No, because remember you're summing rectangles, so it's going to find rectangles all the way to the point of discontinuity and then keep going. So they don't care about discontinuities, which is kind of nice. Infinite discontinuities, that's the only different one, but we'll get to that. Min and max equality. Okay. Can I give an example of an integral with a function? Yeah, I mean, literally any piecewise function, Asma. So like if you have like literally any piecewise or anything with a hole would work. All right, max and min inequalities. Okay, this one I'm gonna need a demonstration for, because it's like a whole thing. All right, let me get that ready for you guys. Share this one over here. Okay, so let's say I had the function sine of x. That's a good one. Okay, and I will actually, let's just look at sine of x from 0 to 2 pi. There we go. Let's just look at, oh boy, that is the wrong color. Sine of x is not red. That's better. Okay. Now an integral is the area under the curve. That's what I've said, and that's what I'm sticking with. I'll watch you guys. There you are. Okay, so here's my question. What is the integral of sine of x from 0 to 2 pi? What do you guys think?
Is it going to be 0?
Why?
Because you have the area from the area from 0 to pi will equal to the area from pi to 2 pi, right?
Yep, absolutely. So the area above the x-axis is positive, and the area below the x-axis is negative. Notice they're the same, so they cancel out.
So what does it mean in terms of distance? Are we
It's-
saying if someone is going forward and then going backwards
Yep.
and basically has not moved?
Correct. Yeah. Yep, they're back where they started. It'd be like if I walked to my front door over there and then walked backwards over here.
Okay.
Yep, I've traveled all that distance, but I didn't move from my starting position. So here's my question, this max-min inequality. This is what it says. The integral will always be between the minimum value times b minus a and less than the maximum value times b minus a. So here's my question. Ready? What is the maximum value of sine of x?
Pi 2.
That's an input. What's
1.
the output?
1, yeah.
1,
1, yeah.
1. So
1.
so let me get if this one, nope, integral function, this one, 1, 0, 2 pi. Okay, so if I graph the line y equals 1 and then found the integral from 0 to 2 pi, or found the rectangle, right? The height, the max times the distance would be this. Do you agree that sine of it, the actual integral is less than that? What's the actual integral? What's the value of the actual integral?
0.
0. Yeah. And if I did the max value, which is 1 times b minus a, I get what? What is 1 times 2 pi minus 0?
1 pi times
What's 2 pi minus 0 times 1?
1 pi, right?
Max of f times b minus a. So what's b minus a? What's a?
0. So
What's
it's
b?
2 pi.
So then it's 2 pi minus 0 is 2 pi times the maximum of f, which is 1,
1.
which is 2 pi. Now it also says that the integral must be bigger or equal to the minimum of f times b minus a. And what's the minimum of f?
0.
-1.
Negative 1
Yeah.
times 2 pi. Do you agree that this integral is between negative 6.28 and positive 6.28?
Yes.
Absolutely. Now, this
Yes.
becomes very useful when you can't evaluate an integral, but you just need to show it's between something. So you
So
make it,
if we were to get like a trigonometric function to find the interval of, the best probably course of action would be to draw it.
yeah,
Using like
see,
like Ohalo and like trying to like figure out what
Right.
cancels, what areas cancel each other out on that interval.
you got it. So let's try another one. Let's just let me make sure this theorem works. Negative x squared plus 1. This is like, whoa, that's not what I meant to do. Okay, this is one of my favorite ones to do. I really like doing x squared because it kind of works for a lot of things. All right. Now, I want to find the integral of this function. Let's do between negative 1 and 1. Okay. The integral is 1.3. It's 4/3. Okay, that's the value. Pretend we didn't know that value. Right? Pretend we didn't know that. Actually, -1 to 1 is too easy. Let's do -2 to 3. Yeah, let's get weird. There we go. All right, that's the integral. It's the area between the curve and the x-axis. From right here, it's negative. Right here, it's positive. Pretend you didn't see the actual value. And over here, it's negative. Is the entire integral going to be positive or negative?
Negative.
Right? There's more negative area than there is positive. Absolutely. Which means I'm actually behind where I started. Right? If you were to integrate. Now, the way the theorem works, it's max times b minus a. Between -2 and 3, what's the maximum output?
One.
1. And so 3 minus -2. So my max value is going to be 5 times 1. Does that make sense?
Where are you getting 5? I'm
It's
sorry.
b minus a, 3 minus -2.
Okay.
So that's the maximum value of my integral, possibly. The minimum is going to be, again, 3. Well, I don't think it's going to like that. Oh, no way it did. That's neat. Okay. Times the minimum value. What's the smallest value of -x squared plus 1 from -2 to 3? I think it's like -8.
-8.
Yeah. That means my integral is between -40 and 5. Which it is, -6. It does not mean it's an average of the two. It just means it's guaranteed to be between. It's kind of like the IVT, kind of.
So what if we didn't have a graph? How would we determine it? We would have to integrate as a function, right?
No,
plot
so
in-
if you integrated it, that will give you the actual value. But if it wants to know, like, use the max min theorem, you would actually take a derivative of it to find the max. And then, like, does that make sense? You take the derivative, set it equal to 0. That will give you your max coordinate, plug it in, that kind of stuff. Or just kind of know what the graph is. You have to, like, know, oh, -x squared plus 1 looks like this, shifted up by 1.
So, but we're going backwards. So we really, when we integrate, we're getting a cubic function.
Right, but integrating this will not tell you the max value.
Okay. So if we set the function, okay, okay, I get it. So
Yeah,
it's like the reverse of what we were doing with derivatives when we were finding f1, f2, and then finding using those to find the max, right? Or
I don't know if I would call it the opposite or to do max and mins. So like if you had a really complicated problem and you had no idea what the max would be, you would take the derivative and set it equal to 0 to find max and mins. However, typically when they give you something like that, it's like a close enough to a parent function that you can usually find it pretty fast. But all right. That's enough for that, the max min stuff, because it comes up, but it's rare, but it comes up. Okay. You guys are going to like the next part. The next big chunk of this is more algebra based. Okay. Oh, yeah, we got to do 3D as well. Forgot about that. Okay. So I'm telling you, that's a fact, that's a fact, and that's a fact. I don't know what the functions are. I don't know what they are. I just know the integral from -1 to 1 is 5. I know nothing. I know nothing of this value. It's not half of 5. Be very clear about that. Just because it's half the distance does not make it half of 5. Right? Because your functions can go like for example, -1 to 1. It could go like this. Right? So just because it's broken up in half does not mean it's half the integral. Okay, determine the integral from 4 to 1 of f of x. Well, if I know 1 to 4, and I want to know 4 to 1, I can actually flip this integral and just put a negative in front of it.
Yep.
And then do I know this portion of it? What's the integral from 1 to 4?
It's -2.
No, so it's negative 2. So then your answer is 2. And you're done. That's it.
Well, this is easy.
Yeah, I think so. All right. How about the integral from -1 to 4 of f of x dx? So I don't actually have explicitly written -1 to 4. However, using my rules, I can split this up
Oh,
-1 to 1
mhm.
and from 1 to 4,
Yeah, that makes sense.
right? Because if I add these together, I get that back. So the integral from -1 to 1 is 5, and the integral from 1 to 4 is -2. So the integral from 1 to 4 is 3. How do we feel about that? Nice. All right. Since you guys are so confident, your turn. I'm gonna give you 2 minutes. All right, if you can answer that poll, whether you're done or not, just to see where we're at. All right, looks like most of us are finished or stuck. My 2 favorite answers. All right, so let's go over them. Step number 1 for this, you want to go ahead and distribute that over the integral and bring out the 2. So then the integral from -1 to 1 of f of x was 5. So 2 times 5 plus 3 times h, which is 7. So 10 plus 21 31. Nice. 0 to 1. I don't know this at all. Not enough info. Can't solve it. -2 to 2.
Not enough information.
Same thing. Now this one, the first thing I'm gonna do in the last one is I'm gonna go ahead and split it up. -1 for h of x dx. Now this f of x1, I can solve that, right? By breaking up the integral into two pieces.
Yep,
This one I can't.
exactly.
So same thing. Can't do it.
Yep.
Not enough info. Cool. That's it. So those are some limited.
I have a question.
Yeah.
When you split the integral, so first you're doing from -1 to 1, but then, so you're looking because from -1 to 4, that is 5 units change, right? And I don't see how we can do it.
Can't do which one? The -1 to 4?
Yeah, how would you split it? Because
Like
I
that?
don't,
Like that in part B?
oh, okay.
Because these match.
Yeah, okay, and then, okay, yeah, I just, the numbers were just, my eyes tricked me. Okay, got
Oh,
it.
good. All right. So we've talked about average rate of change. Well, before I get into that, what's average rate of change?
dy dx. No, it's f of a minus f of b over b minus a x. Yep. F of
All
b.
those things, right?
Yeah.
Yes, it is. She asked, is not enough information a possible answer? And the answer is yes. It'll be one of the multiple choice answers. Yeah, it could be like A, this, B, this, C, this, and then D be not enough info. If it was a question like that, they could do that. Now, so this is your change in Y divided by change in X, right? That's what slope is.
Yep.
And we call this average rate of change. Now, the reason I'm taking a minute to actually write all this out, let me write it this way. Average, I'm going to write a little neater. You don't have to copy this if you don't want to. Okay. Delta Y over delta X. All right. Which part of the delta Y over delta X is the change? And which part is the average? If you want to break up average rate of change into like the pieces of the fraction, which piece makes it an average and which piece makes it the change?
B minus a makes it average.
Okay. The average is that part, right? The change is that part, right? If I told you you got 100, a 50, and a 75 on a test, on tests, how would you average them?
You would add them together and then divide by 3.
Right, you would add them up and divide by the number of things you added. Okay. Now we're going to get into what's called average value. Average value. And the way this works is, if I wanted to find the average value of y equals 5 from 0 to 5. So I have this graph, looks like this. And I want the average y value. Well, what's the only y value?
It's 5.
Yeah, so the average Y value would be 5. Okay. What if I asked you to find the average value of Y equals X from 0 to 5?
You have to use all the points.
5. Right? You would add them all, add up the points and divide by the numbers you add. Now it turns out, guess what? It's 2.5. That makes sense that the average number is the one in the middle. Right? Because like these two are going to cancel and then those two, right? And so on. Okay. Linear functions, not so bad. What if you wanted to do the same thing for x squared?
In trouble.
Right? So you could approximate it by picking values. Maybe you break it up, you know, into 5 points and then average them. But the idea is I want to add up every single one of them, every infinitely many of them. So all we do, you do this, because an integral is going to add all of my y values, right? It adds all those rectangles up, and then it divides by b minus a. So you're averaging all of the y values. Because remember, an integral is an infinite sum. So you're summing up all of the y values and then dividing by b minus a. That's average value. We'll teach you how to integrate. Okay. All right. Thumbs up if you, or not thumbs up, I'll do a poll. If you understand the idea behind average value, and a 1 is like, not really. Okay, a little iffy on it. All right, all right. Well, then we can fix, I can fix that. Well, I can try to fix that. Okay, so I'm going to give you guys a graph right now. This one right here. And we're going to look at it from 0 to 3. Right here, right here. If you had to guess what the average Y value is between 0 and 3, I want you in the chat, don't type anything yet, don't spoil it, but in 10 seconds, I want you to use your gut reaction. What do you think the average Y value of this is? Right, if I'm between here, okay, go ahead in the chat, push enter, push enter, push enter. I want the average number. Let's go, let's go. 2.5, 2.5, 1.5, 3-ish. Okay, so it's interesting because nobody put this. Oh, issues, some people did. Nobody put that point. Right? Nobody put, a little less than 1. And nobody put that.
Yeah, because it's a big.
So average value likely is going to be in between your smallest and biggest point. Now, why did nobody even went above 3? Why did nobody go above 3? What was the rationale? Even if you don't know. Instinctively, nobody put above 3.
Because it went down after 4 and you had to account, and then it started low. So
yeah, so like maybe a lot of these values kind of cancel out like some of these values.
Yeah.
It's kind of like the logic, right? So you have like maybe this many above, but then you have this many down here. So your average, I lost it. It's probably somewhere in the middle. So we're gonna use calculus. We're gonna add up I lost my number here. We're gonna add up every single value. Get out of here. We're gonna add up every single Y value and then average them. Sorry, my cat's been pretty good for the whole session. She's a little needy today. I don't know what's going on. It's weird. I'm home all day today. I'm normally not home all day. And she's needy today. She ignored me all day. I don't know if any of you guys have cats. They're temperamental sometimes. Okay. So, where's this button? This one, this one. Okay. So here we go. I'm going to teach you how to do an antiderivative. Before I teach you the antiderivative, if I wanted to find f prime of x, how do I do that? Slowly, how do I do that?
Find the derivative.
Okay, a little faster. How do I do it?
You said, take the highest term, x squared, and then move it forward.
Okay, you
Yeah,
take
2x.
that, drop it down. Yeah, you take these, drop it down, and -1, right? That's the power rule. So an antiderivative reverses it.
Mhm.
So I'm going to add 1 and divide by the new number. Add 1, new number. So if I want to, I'm going to integrate from 0 to 3 for 1, 3 minus 0, 4x minus x squared dx. So 1/3. This is going to be 4x squared over 2 minus x cubed over 3 from 0 to 3. And that's the notation. It changes from that squiggly to a straight line on the right. That's the notation that says I have integrated. So again, I took the exponent, added 1, and divided by the new number. Added 1 and divide by the new number. Okay. Then what we do is we take this 3 and we plug it in for all of our x's. So it's going to be 1/3 4 times 3 squared over 2 minus 2 cubed or 3 cubed over 3 minus when you plug in the bottom number. I know, it's going to go to 0. I know. And that's how you integrate. This is for the integral of f. So this is what we're finding right now is 1 over b minus a to b, f of x dx. And sometimes you'll see that written as 1 over b minus a times capital. Sometimes they represent the antiderivative as the capital version of it. And then if you do 2 integrals, we run out of things to call it. So then this is 1/3 times 36 over 2 minus 27 over 3 minus a big old 0. 1/3. Yeah, we're finding average value. This is 18 minus 9. So 1/3, 9. Now, ready? There's a reason I did not multiply by the 1/3 yet. What does this 9 represent before I multiply by the 1/3?
It's also. Is that the of value
Yeah.
of the rectangles that the x which are bigger than the actual? It's R. Is it R RAM?
No, it's not RRAM. It's not LRAM. It's the
Okay.
actual area underneath. So
Okay.
this 9 represents the actual area underneath this.
Okay.
The antiderivative, yes, the antiderivative before I did the average, exactly. Now to be clear though, what this 9 also represents is all of these y values actually added together. So if I added 0.5 plus 1 plus 1.5 plus 2, 2.5, 3, and so on, all of them, infinitely many of them, I get 9. And this is something that's like super cool and super interesting to me. We just added an infinite number of numbers and got 9. right? We added every single one of these y values. Every single one of them. And got 9. I know that doesn't sound like something. The saying it out loud and saying it more loudly and repeating it doesn't, I guess, make it more interesting. To me, it's super interesting. The concept that we just added an infinite number of terms, like it's insane. Okay, but yes, Maria, the area, exactly. So that's my integral. Now, I have to divide it by 3, right? So I'm trying to find average value. So I'm going to average all of these values. And that's where this comes in, this button, this button, this button, that button. So then this is going to be equal to 3. So on the interval 0 to 3, the average output is 3 of that function.
So that means the average.
Value.
The average with respect to the rectangle, the area.
You want to start getting away from the rectangles. It's just the average y value, the average output of that function from 0 to 3 is 3.
Okay.
And the way where this comes into real life, if you want to find average temperature, or if you want to figure out like, okay, your car engine was on for 10 hours, what was its average temperature? What's its average running temperature? You do something like that. And you can usually display temperature as a function of time and yada, 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 right? Okay. All right. Mean value theorem. All right, here we go. You thought you were done with this theorem. What happened? Well, that was weird.
Real quick, so the antiderivative, what does the antiderivative stand for?
Okay, so it depends what dimension you're in, and it depends what the application is. And I know that doesn't answer your question at all. So if it's the antiderivative of velocity, it's your change in position. If it's the antiderivative of acceleration, it's your change in velocity. If it's the antiderivative of position,
And what is that?
yeah, it's a thing. Typically we don't just take the integral of position without dividing by b minus a to find average position. Some people consider it the next dimension up, which is time space. It gets kind of weird into that kind of stuff. If you integrate a line, you get area. If you integrate area, you get a volume. If you integrate volume, you get a problem. It's kind of the phrase. Yeah. Once you integrate volume, you're going into the 4th dimension, and then you get all kinds of weird nonsense.
I hope this is not too much. Is there any way you can write that down, like volume, arrow?
Sure. Ready?
Area?
You ready? Yeah.
Yeah.
Good. So I'm gonna write line. It's not line, it's 1 dimension. Like, if you have like something like this or a curve, right? And then I'm gonna write 2 dimensions. This is area, and this is volume. If you take an integral, it goes this way. If you do a derivative, it goes out. Same thing with position, velocity, and so position is here actually. Velocity and acceleration. Oops. No, that's right. If you integrate, it goes that way, and the derivative goes that way. Yeah, and when we get to the word problems, it blends these together, and so we'll talk about that more. All right. Do you guys remember the mean value theorem for derivatives? Average rate of change must equal instantaneous rate of change.
Yep.
Okay, it's the same thing for integrals, but different. Average value has to equal actual value. So remember, a derivative is a rate of change. average rate of change equals instantaneous rate of change. Well, mean value theorem for integrals is average value must equal the actual value somewhere. Do you remember the graph that we looked at, the 4x minus x squared? Remember that looks like this? Something right here. That one? Oh wait, it don't look like that. It actually looked like that. And the average value was like 3. Is there somewhere between 0 and whatever that was, such that the y value was actually equal to 3?
Yeah.
Yeah. That's what the MVTs of integrals say. The average value will equal the actual value. Same way with MVT for derivatives, average rate of change equals instantaneous rate of change. So very similar. You set it up the same way. Actual value, an output, equals average value. So here's my question. Oh, it has to be continuous on a closed interval, that kind of stuff for MVT to work. So here's my question. What X value satisfies the MVT for, I think that was the function on the interval 0 to 3. So basically we're just going to use this and figure out the X value that makes it work. So if you ever see what X value or what C value or prove for the MVT, f of C, this is what we're solving for, equals 1 over b minus a integral a b fx dx. What's a?
0,
What's b?
3.
Okay, so f of what, or c, right, equals 1/3 integral 0 to 3 4x minus x squared. Now, we just integrated that, so I'm not going to reintegrate it and do all the work. I think we got 9, 3. Well, I'm going to write 1/3 times 9 just for fun. All right, great. That means my average value equals 3. But I want to know for what x value does the actual function equal 3? So f of c is just 4c minus c squared equals 3. Plugging in c for x. You can leave it as x. It doesn't matter. Now,
Okay, makes sense.
yeah, move everything to one side. And we're going to solve. C minus 3. C plus 3 again, or plus 1. No, yes, no, minus 1. So C equals 1 and C equals 3. So in fact, there's 2 places. Cool. It guarantees there's at least 1, but we found both.
So you don't have to actually integrate, use integration in
Well,
here.
we did. We did that from here to here. I did it up here, so I didn't want to do it again.
Oh, so you did, okay.
Yeah, I just don't want to do it again. But they could say, what value am I guaranteed to get of f, or no, will f of x ever equal 10? And it's like, or actually, if they worded it for this one, they will say, will f of x ever equal 3? Did that make sense? And then you could find the average value. And then you get 3 and you're like, oh, yeah, somewhere. I don't know where, but somewhere. You can also use IVT, I guess, for this one too, if you didn't want to integrate. But sometimes you'll only have the antiderivative values.
So that's why it has to be continuous, because if you want to get a point where it equals the average value of the, antiderivative,
Yeah.
right, there has to be a point. Like if there just somehow that gap exists where 3 was, then there would not be an x value that satisfies, right? So it
And you're
has to
not
be
guaranteed.
continuous.
Yeah, and you're not guaranteed it. Because,
Okay.
for example, if I had a function that looked like this, which I think we should know this one, right? This is the integer function. Actually, it technically isn't. I drew a different one. I technically drew this one. but whatever. Say we have a function that looks like this, and you can actually find the integral of that by finding all those areas. Right?
Mhm.
So that's 1 and 2 and 3. The MVT doesn't hold because I'm only, you know what I mean? I'm missing all of these X values.
Mhm.
I mean, the Y values. I'm missing all of these Y values. So I'm not guaranteed. I'll actually never get 2.5. So say I average it and it's 2.5, I'm not guaranteed to get it because it's not part of its range. So that's where the continuity has to come in. All right.
I have a question.
Sure.
So if it's a continuous on a closed interval, so you're finding that C could be the average value can fall at C equal to 1 or or
3.
3, and 3 isn't, so so C was our limit, right?
C,
mean, I-
C is the X values.
Yeah, but it's the upper limit. So, but it's still, we can have C as the value.
Yeah, that's a complete coincidence, but yes.
Okay.
Yeah, you would never get C as like 4. You wouldn't get that.
Yeah, that makes sense. But it has to be
Well-
between, or it could include,
Endpoints it can include.
yeah, it's an endpoint, yeah.
So as when I brought up the IVT, I worded the problem different. I said prove that 3, you must have an output of 3. And so if that was my whole goal, just to prove I had an output of 3, I would just find f of 0 and f of 3 and evaluate them. And so here I get 0, here I get 3. IVT, it guarantees I get every number, including those in between. That's I changed the problem when I made that reference though. I changed what it was asking for. All right. Moving on. All right, this one's a big deal. And what about what's written here makes it a big deal? There's a word on the screen that says this is a big deal.
Fundamental.
Fundamental.
That's right. And don't I call this one part 1. Some other books call it part 2. It doesn't matter the order you do them in. I do them this way. The fundamental theorem of calculus part 1 states that the derivative of an integral is the function itself. The derivative of the antiderivative is just the original function. So this represents capital F of X is the antiderivative of that. Right? From A, which is a constant, to any value X. The derivative of the integral is the function back. And if we think about that, if I take X squared and I integrate it, I'm going to get X cubed over 3 plus some constant. We're going to talk about that plus C later. Don't you worry. Now, if I take X cubed over 3 plus some constant and I take the derivative, what's the derivative of X cubed?
3x squared,
Power 3x, yeah.
And then what's the derivative of a constant?
0.
0. So look, the derivative of an integral is just whatever that function is back.
Yeah.
But this is a big deal. Like, I know it's like, duh, but like, this is a really big deal because now you can take the derivative of an integral without having to do any work. You just cancel them. And I know you're like, duh, well, of course, but it was a big deal when this came out. Okay, this was like a bigger deal than like Taylor Swift's like most recent boyfriend. Like, this is a big deal. Okay.
How, it's probably too long of a question, but I'm assuming that they had to prove without
Yes.
solving every derivative,
Correct.
right?
Yeah.
Okay. Because it's impossible to solve every derivative.
Which is my favorite book.
What is that?
This is my maybe I should get I'm gonna see if I can get
The reading list or something?
see if I can get a PDF of this. This is called First Course in Real Analysis. This proves calculus.
It's like I'm not gonna be able to understand it.
No, you will. So like for actually no way, I just opened up the right page. Oh my god, I did. Hold on. I think I have the proof right here. This is getting into it a little bit into the weeds. Right there. So that talks about taking the derivative of the integral and you get the original back somewhere like right there. Yeah, oh my god, look at this. Right there. Fundamental theorem of calculus. Right there. Fundamental theorem of calculus. The derivative of the antiderivative is the original. Good stuff. Anyways, one of my favorite books. But yeah, so it's a big deal, and we prove it from scratch, which is like a lot of fun. But that's, you know, we can't go there. Drop the book in the chat. It's okay. So you can. There's many authors, many authors of real analysis. This one's by. It just says the first course in real analysis. So first course in real analysis. This is like the first big kid math. It's 2024, so I can't say big boy math anymore. This is the first big kid math book. So you take a course called Introduction to I call it Introduction to Actual Mathematics, but it's Introduction to Higher Mathematics is the course you take before it, and it teaches you how to write proofs by induction and by all that stuff. And then then it breaks off to like linear or what is it? Not linear algebra. Shoot. I forget what it's called, but you prove linear algebra or you prove calculus. Those are the two courses that you branch off to. That's the one where you prove calculus. So everything we've done in this session or in this workshop, I've had to prove from scratch. And you get to start with the only thing is the definition of a limit. That's it. That's all you get. Every other theorem, every other thing we've done, we've had to prove from scratch. And you can't use it until you prove it. And so it's been like a lot of fun. You couldn't even use that 2 + 3 is equal to 3 + 2. You can't use that you can add in either order either. You need to prove that first. Anyways, it's a whole other rabbit hole of stuff. Okay. So the reason I bring this up is we're going to take the derivative of this integral. You ready? You guys ready? Because it's going to happen fast. Is this a constant?
Yes.
Cool. Put that in there. We're done. That's it. That's all there is to it.
Wait a second. Wait a second.
I know. Don't believe me. I know. But that's it. Wait, why is this all worked out?
I don't understand this. Hold on.
So, you know, if you had like x 5 times 5 and then divided by 5, they cancel each other.
Yep.
It's kind of the same thing. The derivative and an integral cancel each other. It's like the opposite operation. It's not the opposite. It's the wrong word for that. But in your brain, you can kind of think of it like undoing it.
Oh, okay. It's like, okay, I get it.
The same way, if I had this, they cancel. Now, we typically write the ddx over here, don't we?
Yeah.
Because we do the antiderivative, they cancel.
Okay, I get it. Okay.
Yes, Asma, I'm happy to show you. Let me get through these and then I'll show it to you. No problem. Okay. Now here's the catch. Notice how this is not just x.
Squared.
So let's first start with this. Is this a constant down here?
Yes.
Sweet. So you're good. So these cancel. This goes into there. 1 over 1 plus x squared. But then this is where the chain rule comes in, because remember, we're taking a derivative times the derivative of the thing you plugged in. That's the chain rule in action. Because we're still taking a derivative. Now, before I work this one out, actually, we'll work it out just because we're like right here. And we're like almost done. There we go. Now, did I do the chain rule in this example?
The first one?
Yeah, did I do the chain rule?
Yeah, but it was, you
Yeah, well-
didn't have to because it,
1.
Yeah, what's the derivative of x? It's just 1,
exactly,
so I don't bother writing it. But I do want you to see it was still there.
yeah.
So it's not like we're like, I chose like, oh, all of a sudden he's adding rules. No. The rule was there before, but like, we just didn't have to do it. Okay. So the derivative of an integral is just itself times the derivative of the upper limit. Okay. All right. Give those a try. Oh my God, we only have 15 minutes left.
Oh my God,
I know.
it went very fast.
We didn't even get to the good stuff. Oh, I didn't put a timer on. Let's say 2 minutes. Oops, I guess that's too much time. There we go. And then as I'm working on a graphical representation, give me a sec. I'm working on it. Actually, I think I got it. Let me see if I can get the more complicated one though. I can show you the graphical representation without the chain rule. All right, we're gonna go over these. So let's do the first one together. Okay, all you have to do, right? Take this in there. So it's gonna be cosine of x squared times the derivative, which is 2x. We're done. That's it. Okay, the next one, same thing. Take this in there times the derivative of square root of x, which is that. And we're done. Cool. Before we move on, though, I do want to show that graphical representation of the thing. So say I have x squared. If I integrate x squared, I get this. And this is what I mean by plus or minus the constant. Right? That this is that plus c. And if I take the derivative of g of x back, look, I get x squared again. No matter what my c term is here. So does that make sense? So if I start with this, do the antiderivative, I get something cubed. take the derivative again, I get x squared. So I get the returning thing back.
Curious, how do you move the functions, in GeoGebra?
I added a slider called A, and then I just added the A on the outside.
Oh, okay,
You
thank
can
you.
animate it. Yeah. Alrighty. So let's go over the next example, which is when this thing becomes a problem. Like that. Why can I not take the derivative of that integral written as is?
Because we have we have the 2x and x squared, and they're variables.
Yeah, exactly, right? So the integral does not have a constant. Well, okay. Like we can make that happen. It's all good. 2x to 0 plus 0 to x squared. Remember the rule? The top and bottom limits just got to be the same. Pick your favorite number, doesn't matter. If you want to be more mathematically correct, you should find somewhere an x value where they intersect. Really should, but that's here nor there. It really doesn't matter. For the sake of this test, let me rephrase that. If you were really doing this like in a math course, you want to find out where they intersect, and that's the x value you pick. But watch why it's not going to matter. When I flip this one, e to the t, why does the constant I pick not matter? Why does the constant I pick not matter?
Because when you take the derivative of it becomes 0.
It goes away. Exactly. Mathematically, this value here should be where those two functions intersect. However, it's one of those things when you just solve them, it doesn't actually matter. For all we care, you could have put the letter A. Okay, so take the derivative, I get negative. This thing goes into that x. 1 over 2 plus e to the 2x times 2. And where did that extra times 2 come from? Where did this thing come from?
You have to take the chain rule.
Yeah, the derivative of that upper limit, which is why it's important we separated it and then flipped the integral, because now we're going to have a negative sign. So plus 1 over 2 plus e to the x squared times 2x. And then we just write our answer all nice and pretty. And you can't combine those fractions because they have a different denominator. All right, we got one more thing we're doing tonight, and then we're done. One more thing. We're going to learn fundamental theorem calculus part 2. Or some books call it part 1. This is considered the useful theorem. The other one is like theory, the derivative of integrals itself, that's more theory. This is the one that you put into practice almost every single time you do an integral. This part, you don't actually technically need to do integrals, but for the fundamental theorem, will always guarantee this is true if it's continuous. When it gets discontinuous, things start to get weird. To be honest, we just break it into its continuous pieces. And that's how we do it. So that's why you're allowed to integrate over non-continuous functions. But for continuous over a closed, this will always be true. So when we integrate over non-continuous functions, we just integrate over the continuous portions and add them up. All right. All this means is you do the antiderivative and plug in the endpoints. We've already done that tonight. But there it is as a theorem. Okay, there it is as a theorem. That's all it looks. Okay. Let's put that in practice. Here we go. Ooh. You'll see me start to drop these parentheses, but technically they're there. So like if I wrote this, I'm not integrating that x. It's only integrating what's in front of the dx or between the integral and the dx.
Hmm.
So the way you integrate with powers is super easy. It's reverse power rule. Add 1, divide by the new number. Add 1, divide by the new number. So what's 3 plus 1?
4,
Nice. 1 plus 1.
2. over
So
2.
this becomes x to the 4th over 4 plus x squared over 2 from 0 to 1. This right here is the antiderivative if this is f of x. Then what you do, you take the 1, you plug it in. 1 to the 4th over 4 plus 1 squared over 2 minus when you plug in the lower limit. 0 to the 4th over 4 plus 0 squared over 2. And I get 1/4 plus 1/2 minus a big old 0. And I get a nice 3/4. Much, much easier than LRAM and RRAM, in my opinion. Honestly, too, if you do LRAM and RRAM, once you get to like 10 rectangles, your approximation is going to be like say you did 10 rectangles, you'd probably get 0.73 or something. Like you're going to get really close. You probably actually get 0.756, something like that. It's crazy how little amount of rectangles you need. All right, let's try it with this one. This will be the very last problem we do tonight. So the antiderivative, add 1, divide by the new number. So it's going to be 3x cubed over 3 plus 2x squared over 2 from -1 to 2. Again, you're taking the power, adding 1, and dividing by the new thing. So these are going to reduce off. That's nice. So it's going to be x cubed plus x squared from -1 to 2. Now you take the 2 and you plug it in. So you get 2 cubed plus 2 squared minus when you plug in the lower limit. -1 cubed plus -1 squared. It's a coincidence that it's going to make 0 again. 8 plus 4 minus -1 plus 1. And you get a nice 12. Integration, super easy. Until you get all the rules. Oh, sorry. Before I move on, though, let me know 1 through 5. How you guys feeling about that? The stuff we covered since I've asked you last. All right, cool. So what I want by the time you come to class on Wednesday is to look over all of these antiderivative functions. And then we're going to get into integrating. Okay. If you think about it, it's the reverse of a derivative. That's it. So like the antiderivative of cosine is sine.
Yep.
The derivative of sine is cosine.
Mhm.
Right? So that's honestly how I remember learned most of my integrals is by remember them backwards. But I think what is it the derivative of?
It's
Or-
almost like multiplication and division, right?
They have a very similar, they kind of like undo each other. Yeah.
Yeah,
They're not opposite because opposite is a negative, but
yeah.
very similar. Okay. A lot of stuff. Tomorrow we're gonna get into some U sub, integration, some volumes. It's good stuff. Not tomorrow, sorry, Tuesday, Wednesday. No, we don't have to integrate inverse. I lied. Yes, we do. Yes, we do. And remind me to add that first thing on Wednesday. Actually, I guess I can just write them right now. Might as well just write them right now, huh? So they're, I don't think these are on the website, so make sure we get these down.
Oh, the
Yeah.
arc sine, all those.
Yeah.
Okay.
Integral, tangent, inverse. And then the other three don't come up very often, but I'll get them down. I guess I'm right here, might as well. See if I remember on top of my head. Secant, inverse. If you'll notice, they're very similar to each other. Got them all. My hint was with anything with a co is like itself, but with a negative. So cosine is like sine inverse with a negative. Cotangent is the same as tangent inverse with a negative. Cosecant is the same as secant with a negative. So you'll notice they kind of like pair up together. And that does,
So,
yeah.
I'm sorry, just a real quick thing. So the inverse tangent function, isn't that just the inverse sine divided by the inverse cosine? No? Okay.
I wish it was that simple.
Oh, okay, never mind.
Although now that I say it out loud, I've never thought of it. I don't think it is. My gut said no, but like,
It's not looking at it a little bit longer. It's not.
you sure?
Are you sure?
I hope not.
It's-
It might. No, right? No, I don't think so. I really got to think about that
When
now.
you divide those fractions, I don't think you get that
Yeah, right.
denominator at the end.
Yeah, but when you integrate, you can't integrate over division anyways.
Right.
So maybe I don't know. I got to think about that now. That's a good thing to think about that tomorrow. I'm gonna go ask a math professor.